All right. Yeah, welcome back to our panel discussion on quantum fault tolerance. So we will have actually panel discussions most days. So again, today is kind of centered around what our three great speakers talked about. So that was like the present and future of quantum fault tolerance and like what the key challenges are. I don't know whether people have kind of picked up on it, but there's an interesting Venn diagram going on here. So there's two people are pairing up in terms of being a theorist and one experimentalist. There's two people representing QLDPC codes. One is representing surface codes. And there's another pair of architecture. So there's like superconducting architecture and then neutral atoms, of course. Yeah. So there's an interesting kind of Venn diagram. So this should kind of give us like some like diversity of opinions. So let's kind of, I hope we can kind of explore this. I will maybe ask some questions in the beginning to kind of warm everybody up, and then I will kind of open it up to the audience to ask questions. And yeah, the first question I have is essentially, just to kind of kickstart things off, is like what do you see as like the primary challenge within the next 5 to 10 years? So what you think are the most pressing questions that need to be kind of answered within the next, yeah, really 5 to 10 years, like midterm. Yeah, so whoever wants to go first.
Yeah, so yeah, I think that in terms of like things that are experimentally relevant, I think stuff like what IBM did with this Tour de Grosse paper, or what Craig and other people on our team have done with these other architectural papers, like starting to lay out full end-to-end protocols of like how you would handle an entire algorithm, I think is really important, because that kind of checks for any gaps. Because the way I see it is like the next 5, 10 years are where we're really going to start approaching actually being able to do some stuff. Maybe not like full fault-tolerant simulations or factoring or anything, but like at least sort of small prototype versions of that are really coming into view. And we're going to need to now start figuring out like what is the missing piece, what's like the weak point that we need to bring up as a field. And I think to do that we need to really like, our field's done a lot of work in getting each individual component really good. But no one's really, or not no one, but like we have not done as much work in plugging everything together and showing that all the pieces fit well and all those interfaces are figured out.
Right. Yes. And I mean, they have probably like one aspect of this is like, I mean, this is like probably also in terms of theory, but also experiment, right? There's like a gap between theory and experiment, but also like a gap maybe within the each like individual subfields of theory. Is it?
Yeah. Exactly.
Yeah. Right.
Hello? Oh, yeah. Okay, it's very soft. So the thing I was thinking about was the scalability of the architecture, and we were looking at these monolithic chip designs, and I guess we have some argument that says, okay, we can't just keep scaling this up because we expect faults to occur, and Dripto has done a great analysis of what we can do to deal with it. But let's say you wanted to assume a perfect chip because maybe you haven't read Dripto's paper. Then the obvious answer would be some kind of modular design. So you have chip yields, and if your chips are of moderate size, you can expect to succeed in some constant number of tries, so like 1 in 5, 2 in 5 times. And then once you have those modular pieces, you can link them together to build, your large architecture. And that's sort of what we tried to do in this Tour de Grosse paper, to see how you can modularize your design, and and how you could scale this further. I mean, there's a lot of other things that come into play, like control system and decoders and all that kind of stuff. So very, very interesting developments.
So a few years ago, I would have said that I think we need to see what it even looks like to do error correction in practice. And I think now we have a significantly better understanding across many different systems. Now I would personally really like to see across all these different systems getting to like 10 to the minus 10 and below errors. And that will, I think, give us, when you can really like start to touch that in the lab, I think we will then have a much clearer footing to stand on for trying to envision large-scale systems.
How do you feel about kind of trying to kind of cut down on overheads at this point, like in like just from like a theory perspective, do you think this should have like a priority or?
Yeah, so the overheads we were looking at, I mean, the Tour de Gros is just the first paper we put out with this architecture, and left and right we're looking and we see, oh, we could cut this, or we could change our assumptions a little bit, and we could get maybe even a factor 2 improvement. But we're really looking for the low-hanging fruit right now, and I think we can get massive improvements, you know, any way you look still. So, you know, maybe that's very exciting because compared to other fields, you don't need to eke out little gains. We're just looking at the big strides we can make right now, you know, to get to 10 to the minus 10 or other goals.
Yeah, I guess I'll say that. I mean, I think for me, it's there's kind of like overhead. I think is kind of a very general term, in that like I think generally what we mean by that is number of qubits, but not all qubits are like sort of made equal. So I think that our perspective is sort of, we think we could build, we think we would rather build, right now at least, we're having, you know, it's hard enough to build a simple square lattice and make it reasonably sized. So for right now, we want to keep things as simple as we can, and kind of like, if we as theorists can have harder lives to make the experimental setup a little bit simpler, that maybe is worthwhile. IBM's approach definitely is more on the order of like, if we can get one more experimental feature that we don't have right now, what we can do a lot with on the theoretical side. So let's explore that as well, which is also, of course, valuable. But I think in the next few years, I'm not as concerned about overhead, at least in like the number of qubits sense, purely because I kind of don't think that the architectures we're building right now are going to be the exact ones we're looking at in 20, 30 years anyway. So it's kind of like, I'd rather focus on trying to get like an end-to-end thing before I worry too much about overhead, as long as the overhead is not so penalizing that we can't do it at all.
I am definitely supportive of less overhead. If that's the question. And I feel, so we made a lot of progress with all these transversal tricks, which were experimentally motivated. And now I think there's been clear significant progress with LDPC codes in the field over the past few years. Also significant progress with making magic. I think with some things, I think we've understood that we've reached like bounds in terms of how good it can possibly be. And then clearly with high rate encoding and also magic creation, there's no evidence that we've saturated those. So I think trying to push those as much as possible, at least in practice. I don't know about it, like, you know, but then yeah, so pushing that is very favorable.
I mean, evidence is a good keyword. So what would you say is like the strongest evidence of like, I don't know, either going like surface code or going like LDPC? Like, do you have like if we have to kind of point to one thing, it doesn't have to be you. I mean, maybe yeah. What would you say is like the most convincing argument for going either way?
I could start, which is I think LDPC is pretty clearly better. I don't know if that's, I mean, I guess it depends on the situation. It obviously depends on the situation, because like Dripto was saying, if the connectivity is so expensive, then it's not worth it. So it always depends on in practice. But if you could do it in an easy way, I think it would sure be nice.
Yeah, I think this is one of like the nice things about like the AMO systems like Dolev is working on, is that they're kind of not at all limited, but with shuttling, you have a lot of games you can play. And so once you have all this freedom, you should take advantage of it to the best of your ability. You know, you shouldn't just waste it. But for a more solid state architecture, there is some cost, whether it's, you know, engineer time or whether it's error rate, whatever, to making things more complex in terms of connectivity. And so that's, I think, when there's now a trade-off that I don't think we understand yet, because, I mean, like, frankly, work like what IBM's doing to actually build these L couplers and C couplers and so on, that really will inform us on what is the penalty, you know, like what is the cost of doing this? Because of course, theoretically, like if you assume everything has the same error rate, then yeah, you should do it. But once we know what the actual penalty is, then I think we can start looking at that sort of trade-off curve.
Yeah, I think, yeah, so we have these like limitations for the chip sizes that we can fabricate. And we kind of noticed that it's nice that we can encode a few more qubits in each chip, because in the end we have a chip of some constant number of qubits and we need to connect them together, and this connectivity is very can be very noisy. We have to still see what's going to come out. So, you know, if one connection can connect 12 qubits to 12 qubits as opposed to, say, 1 qubit to 1 qubit, we think that might be sufficient reason to, you know, go for an LDPC code which has higher density. So that's sort of our perspective for choosing these bicycle codes. Yeah.
Okay. So is it kind of like fair to say, okay, there's like some kind of maybe opportunity cost and kind of whether you want to kind of optimize your hardware towards like one side or the other? Like, is it kind of fair to say?
Yeah, I think so.
Okay. But then like, how would you say, like, what made you kind of come down on either kind of going surface code or LDPC code? Like, is there any? Sorry, I'm pushing the same point, but like, would you be able to kind of distill it down?
What do you think is better, Nico?
I don't know. I might have a favorite. I'm going to say.
I think for us, like we've been sort of on this arc for a while now, trying to like build these systems, and I think that at least as of when we started this path, the surface code kind of being a nice like target is very sort of, at least it's pretty flexible in terms of being like, all right, we know what we're doing, but it's a square lattice. It's kind of easy to understand. Along the way, you can do a bunch of NISQ stuff. So I don't think like long term we're super like diehard surface code only. I mean, like we did a color code paper recently. It would be very natural to. They're very similar codes in many ways. It would be very natural to switch to color codes maybe if that was a reason. If there was a reason to do that. But I think for us it's a lot of like we want to kind of build every piece of it along the way, and the sort of the arc that has the most clear path is sort of to do things we kind of know we can do or have done similar things to, and kind of build along that route.
You want to add to that, Eddie? Or,
Yeah, I guess I'm glad there's concurrent work, that explores other architectures. I think IBM has its own path charted, but we didn't have these gross codes or 2 gross codes a few years ago, and their discovery of like how relatively easy they are to implement did change how IBM was approaching this problem. So nothing's to say that things will not be different in a few years from now if we find something else very compelling. But for now, we have a particular roadmap in mind.
I guess, Dolph, you have been like the most flexible in terms of like which codes you have picked so far. Like, I mean, do you have like a favorite, or do you kind of feel like there's like a certain code or like architecture that you have in mind which might be like most suited for like neutralism? Or?
So I mean, it's hard to say. So yeah, we've studied surface codes, 713 codes, 1513 3D codes, 1664 codes, 832 codes. We've done like a whole series of codes, and every time we've done something, we've learned a lesson. Okay, so for me, so I don't see how I could possibly plan out the next 20 years of what our plans are. So in my view, the goal of doing an experiment is to learn a lesson. And so every code has taught us some type of lesson. Like with the 1664 codes I showed, there's a very high rate encoding. And the lesson was that if we wanted to do leakage removal, it would have been very complicated. Several years ago, we did 832 codes, which had a high rate encoding, and we learned that the in-block gates are super powerful. Or I don't mean anything technical by that. They're very nice. They're very useful. And with the surface code, for example, one of the things that was very useful here is just a very established benchmark. So it's like if you want to compare, you don't have to think too hard how to compare between different systems. So that was very, very useful for just understanding in a very honest and accurate way what's the system performance. So I think, it's true that we're spoiled because the system is so flexible. But okay, so for example, in the near term, I think we should try to do experiments to try to get to 10 to the minus 10 error rates. We will learn stuff from doing that. Similarly, if you want to learn a lesson, you should try to go to the other extreme where you try to have like encoding rates as high as a third or something, and then just see what does it look like to have that many qubits in the system, and then see what we learn. Yes. That would be my approach.
Okay, yes. So you already mentioned leakage, and I think like Dripto also mentioned in his talk like different like error models, like not everything's just kind of poly noise. So what would you say is maybe like the source of noise which kind of concerns you most? We also kind of showed like these kind of like like high energy events. Like are there any types of noise that you feel are kind of concerning and that like maybe the theorists have kind of neglected?
Well, I was going to say leakage, but
Please, I mean, you can elaborate on leakage. Yeah, like why is it bad? Maybe that. I mean, maybe not everybody in the audience kind of knows about it.
why is it bad? Well, yeah, like was shown in Dripto's talk, the leakage kind of falls outside of the models that we usually consider, and yeah, you kind of come up with these somewhat ad hoc ways to deal with it. For us, like we have these automorphism bicycle instructions, and they give a good checkpoint where you kind of measure out the qubit because you're shifting all your logical qubits around. It's kind of like what you're doing with the surface codes, where it's jumping back and forth, and that gives you a really great opportunity to get rid of the leakage. But experiment will show like if we need more or if that's sufficient. We'll see. Yeah.
I was so okay, there's leakage, and in our system, a majority of it is lost, but then sometimes there's leakage to other hyperfine states, and this was something I was worried about for a long time. And in doing experiments, it's an example of things that you have to just do the experiment, because actually we found a lot of those leakage events somehow actually natively convert themselves to loss, which was extremely useful. The other thing is that I think I'm pretty convinced at this point by like using teleportation as a way to ensure errors are removed. It doesn't have to be between logical blocks. It could also be between physical qubits. But doing teleportation between logical blocks, if you do that every few numbers of gates that data qubits experience, then it really ensures all the errors get removed. And at this point, I don't think that we have yet to see evidence of something that we don't understand, like a cosmic ray event or something like that, it's like confusing and we don't know what we're going to do about it.
Yeah, I mean, to the point, I think all of us sort of for leakage sort of basically said ways to experimentally make sure that it's not a thing we have to worry about too much, because I think theoretically we don't want to start measuring stabilizers that look at two states. That's not what anyone's trying to do. I think one example of like sort of trying to get that into theory is like soft information decoding. So I know that on our end, the machine learning decoder that DeepMind put out in collaboration with us took in sort of soft information like confidence intervals of 0 and 1. So instead of just saying, oh, this measurement was 0, that one was 1, it was like this one was definitely 0, this one was kind of probably 1 but kind of close. And because when you leak and you measure a qubit, the two-state like blob in our measurement discrimination kind of ends up staying in the middle a little bit, you can kind of make it looks like a low confidence measurement. And that's like one way that like on the theory end we could try to help a little bit with sort of decoding. I mean, sort of like saying, oh, well, we got this possibly leaky measurement, so maybe that means that there's some correlated Z stuff happening back then. But I mean, all of us are naming ways to just have the experimentals deal with it before we have to get to it, because it is just so frustrating to work with. Other things like crosstalk puts hyperedges into your decoding graph. You don't want to deal with that.
Which I understand is like not as big of a problem in neutral atoms. Is it correct? Like crosstalk, crosstalk's not as much of a concern for you. Is it?
Yeah, that's right. So as long as we keep our atoms far enough apart, we don't see any evidence of correlations between them.
Okay. I mean, you also mentioned. I mean, your talk kind of dealt with manufacturing errors and like how to kind of deal with like the yield issue. I mean, which kind of brings me to kind of scalability. Like, if you want to kind of scale up your system, like, do you see any issues concerning kind of just scaling up? Maybe first of all, like kind of turning into like a modular architecture that you mentioned, Eddie. Like, what do you foresee in terms of like scaling a device?
Yeah, I mean, I think that one of the biggest things I think we'll start seeing is that, especially for these like superconducting qubit systems, at these different points, you have to fundamentally change how you're getting information into how you're getting drive into qubit drives into your things. Multiplexing gets really hard. We don't have the sort of benefit of like this super parallel control like the AMO systems do. So there are scalability things beyond, I think, what we tend to think about in this room of like number of qubits and like number of couplers and 2-qubit gates and so on. And I think those will probably end up being more significant catch points in the future. But I mean, yeah, like yield and things like that also, of course, will limit us. And I think everyone I think will eventually have to go towards something modular. The question is just like whether the individual modules are specialized or if they're more kind of interchangeable, like whatever. But I can't imagine that in 20 years we're building just football field-sized dilution refrigerators with humongous chips inside of them. That doesn't seem like a reasonable outcome.
Yeah, I mean, I guess, you know, how big can you go, right?
Right.
It seems like you can scale your dealing with some faults up to a certain point, maybe. Like, I don't know, when do you decide it's big enough and let's try to link two chips together?
Yeah, I mean, I think that even if you're linking two chips together, if you have each of them individually having some failures, that's like, I mean, I think it depends on like what the sort of, like I've simulated these things up to like 5%, 10% dropout just to like see. Hopefully we're not in that region ever, but like, I think the question is more about like, even if you do have failures, when do you keep a chip and still have it as one of your modules? You know, that's, I think, I mean, like, I don't know, it depends on what sort of yield rates we end up seeing, but in my mind, if we're gonna build some like large just 15 module, it's probably gonna have something wrong with it, you know? Even if it's just a qubit we don't like because like it works, but you know, like, I can't imagine everything working perfectly, I guess.
Do you see any maybe interesting theory questions which would kind of help you kind of reach scalability? Like, for example, like there was this timing issue that kind of came up. Maybe there's like other theory questions that might be interesting.
I mean, improved decoding is a big one. We now have that real-time sort of decoder that we think works in hardware, like with FPGAs. A lot of the decoding works like as in software, but for our platform, we really need something that works well with gateware. So very iterative algorithms, I guess, are maybe not as suitable. If I'm gonna guess for FPGA design, it's more like very highly parallel computation. So yeah, I mean, advances in decoder design that can deal with these large systems. I mean, it's still constant sized, but.
So do you foresee something like, so if you have like some kind of modular system, having like maybe several like scales of like how you kind of deal with error events? Like, did you kind of do like maybe like some kind of very fast, very simple decoder close to chip, and then maybe kind of if that can't deal with something, you kind of go like one level higher? Would that be kind of? Is that kind of what do you mean?
I mean that. I guess that's a possibility, but really, I'm thinking of looking at a fixed region in your device. So, you know, if the region you're decoding grows with the system, then you cannot give as good of a real-time guarantee. So, I don't see that being a scalable solution. But you know, maybe if the probability of such an event is small enough, then it could be feasible. But you still have that real-time guarantee. So yeah, that doesn't seem that likely.
This is a pretty different flavor of theory question, but so I feel like we now have a much clearer understanding of what does error correction look like, especially, and I use the word look like because I'm biased, but we see really like pictures of what the system is doing, and that was really helpful for designing the right types of experimental controls. I am biased, but I don't personally understand what large-scale algorithms look like. I know what they are, but it would be really helpful to understand what they look like so that we can think through what does large-scale control need to look like on the algorithm level. I find that to be a very interesting question. That was clearly really important in the past few years for us, and then I don't even know how to start thinking about what does it look like to do a factoring algorithm.
Right. Do you feel like, in particular in decoding, like, do you think like, you face maybe different challenges? I mean, I guess like for like superconducting hardware, it's speed. But do you think there's maybe something which is kind of hard for you compared to
like with neutral atoms?
Yes.
I think. Well, I guess it depends on your perspective. So there's like decoding of transversal gates could be challenging, but we now actually understand pretty well that it's essentially the same as decoding a single qubit memory. It's just decoding a memory that's propagating throughout an algorithm as opposed to throughout time. So that I don't think is, there's still a lot of progress to be made there in terms of figuring out how to combine all these things, but I don't know if I would necessarily call it neutral atom specific. I would call it more like how to do still good decoding while accounting for things like, you know, hyper edges, but not in a very expensive way. Yeah, I don't know if there's, I mean, we have to deal with loss, but we found multiple ways of doing that. In terms of decoding, what I personally find very valuable is that these algorithmic decoders are clearly very powerful in terms of like, you can guarantee things about them, but machine learning decoding is also clearly very useful. And I would like to have a better understanding of how to combine these two. And in particular, in recent experiments, one of the things we found is that the machine learning decoding was way faster and also had higher performance, and it didn't require us to do a lot of development. That said, every time we did a new circuit, the stabilizers had a different sign, and we had to retrain the decoder, and that was also horrible. So it's having a better understanding of where algorithmic decoders sit, where machine learning decoders sit, and what the kind of continuum sliding scale between them is would be very helpful in the lab.
Do you want to add something? Or, no? Okay. So then maybe let's kind of open it up to the audience. So if there's any questions, maybe Umesh.
I have a question about a general question. You know, there's this usual exploration trade-off. So I just wanted to get your sense of, you know, if you were thinking in terms of, obviously you're thinking about sort of different architectures for quantum computing, but if you were to think about the space of all, you know, quantum architectures, fault-tolerant ones, and so on, what, you know, do you think we have explored a reasonable fraction of them, or are we nowhere close to understanding what, you know, what these architectures might look like? So, you know, not what the missing ones are, but what's your intuition? Have you explored sort of 90% of the space, or 10% of the space, or where are we in this whole?
I mean, I guess I feel like there's much more to be discovered there. You know, we've been very focused on getting a working design out, and something that we believe in that will get us to the, you know, first demonstrations, then maybe the first applications. But you know, there have been such significant developments in recent years that I don't believe that this is the end of it, right? Like, we have found the code that we're going to stick with, or we're going to have bivariate bicycle codes until the end of time. You know, so yeah, I think there's more to be discovered. I don't know if I could pin a number on it, because, you know, if there are infinite families of codes more to be discovered, then is it 0%? You know, I don't know.
I mean, to that same end, I would probably say, like, if I had to put a number like 5, 10%, and that, like, the fact that, you know, even 2 years ago, the surface code, which people have been thinking about for 10, 15 years, we've now found, you know, a year ago we found 3 more circuits. Now we have, like, an infinite family of circuits that are kind of all similar, but you could basically use a random number generator and make new random surface code circuits now. And, you know, I kind of think that's still, like, even with Lucy, it's very structured, and we're probably going to go less structured over time, is my guess. So I don't think we're even at the right, like, paradigm yet, probably. And I think what we end up doing in 10, 15 years is probably a generalization of error correction as we currently think about it, is my guess. And so I would say we're, like, very much, like, even this code that we would probably study the most as a field, we're still discovering new things about regularly. So that makes me feel like there's definitely a lot more to be learned about all of these other codes.
I would also agree that we're at the kind of 10% level, and yeah, both in the error correction and definitely in the hardware, there's still, like, obviously a tremendous amount of progress that needs to be made.
I guess where I was leading with that is, you know, there was this question, what's you know, somehow implicit about you know, what can theory do, or what's left to be done. So beyond just different codes, is how much room do you think there's for this exploration, which is academia sort of tends to do a lot more of that, to think up wacky new ideas for quantum computer architecture. Is that a good use of time, or what do you think of that?
I think it's an excellent use of time, and I think we've barely done any of it. And I mean, all of the experiments we've done, that at least that I've shown with atoms, are on a machine that has organically morphed over time, that was originally built in 2014. I mean, the original parts of it have been built in 2014. Almost every part of it has been exchanged over time, and that we have like duct tape a bunch of weird stuff together to do a bunch of weird stuff. So if that somehow covered the whole landscape, that would be shocking. Yeah. So, yeah, I think it's so obvious how extremely early on it is, I think, and that we need to do a lot of creative exploration. I think another thing is that we also still don't know what we're going to, and this is an obvious comment, but we don't know what we're going to use quantum computers for. So how could we know that we're done exploring? Because what if the application ends up being some hilarious thing that ends up being some extremely important societal application, and we just had no idea that there was this other constraint on it that we could have never imagined. So I don't know.
Yeah, I mean, to that point, I think also one place where academia really, I think, is super useful is in the hardware sort of exploration phase. There's a lot of things that are very hard for us to do in industry. I think industry is very good at like scaling up an idea and then like putting in the people and the resources to make it big and polished and so on. But it's not as good at testing out, 15 crazy ideas and seeing which of those 15 ideas is the one that actually has a chance. So for example, for like transduction, Google had this like prize to give out microgrants, or maybe not that microgrants, to like a number of groups to try and like work on, because it's just not feasible for us to try and hire 15 people to do 15 different transduction solutions, and then 14 of them don't work, and now we don't know what's going on. That's a much more of a problem that academia is well suited to solve. Or like all of these sort of feature testing ideas, academia is very well suited for, and then an industry I think struggles to build for, because we need to have long timelines and things like that.
I think a problem like closer to what I work a lot in compiling. So one of my goals with this paper was to kind of set a baseline that fellow compiler researchers in academia could use to target, say, this bicycle architecture that IBM is going to build in a few years. So then academia can feel like, okay, well, I'm going to, if you are going to improve our compiler, you will know that this will have some application, right? And we're planning to put out some software so you can compare, to our baseline compiler, and show that you have improved it. That may be a little bit of motivation to work on this kind of problem, and we hope to get a lot of community engagement in improving the compiler for these architectures.
There's one question in the back.
I think it gets recorded.
Okay. Great. Yeah, thanks all for the great talks. I guess you've all talked about how you've solved a bunch of problems to get where you are. I'm really interested, what are the limitations that you're sort of hitting right now? If you had to put a finger on maybe one or two, like what's sort of limiting you at this point, or what hurdles do you have to overcome? Or is it just a fight on 100 fronts?
I think that like hardware-specific error models are really what we're spending a lot of time on right now. I used to, when I joined Google, I actually worked on calibration as well as error correction stuff. And a big part of that was making sure that we focused our calibration efforts on the things that error correction couldn't deal with. But that tended up being a large fraction of the things that we could possibly be thinking about, So I think, if we can, on the theory side, talk to experimentalists and understand what are the kinds of things that you see that we don't know how to deal with and don't fit within our kind of very narrow poly error correction model, generalizing that stuff outwards, I think, is very much the limiting factor for us. Like we talk about leakage a lot, but like leakage, crosstalk, like decoding hypergraphs, things like that, I think are very important.
Well, we put out some of these benchmarks now, and having this baseline is great because then we can see what the remaining pain points are, if you want to put it that way. So yeah, I think for us, we want to really improve the logical error rate of certain instructions like the intermodule measurement, because we think improving those will help push up the capability of this architecture much higher. So that's sort of the limiting factor right now, if I have to point at something.
I think with what I showed in my talk, at least, I think with this continuous coherent operation on 3,000 qubits plus all of the ingredients required for universal fault-tolerant processing, I think that with relatively straightforward improvements of like a factor of 2 or 3 here or there, that really seems to make sense. It does seem like we will be able to do experiments to try to make like a indefinitely long-lived qubit and things like that, which would be an amazing milestone on a technological level, and also explore deep circuits. But this machine is, it would be amazing if this type of machine was all we could ever ask for, but that's unlikely as well. So then once we're doing these types of experiments, we'll have to see what the next steps are beyond that. But that will already be so cool. So, and I don't know if there's really any major conceptual hurdles that need to be done, but we have to. It's nice to say that the gate fidelity will get 2 times better by increasing laser power by a factor of 4, but there's always some stuff, and so we'll have to do it. But I would personally be surprised if at this point there was some sort of major unforeseen bottleneck, like some kind of cosmic ray style issue with the system that we just don't understand, at least to get to that scale.
What would you call long-lived qubit in terms of time?
The question was, what would I call a long-lived qubit? And I think I don't know, like doing like 1 million cycles or like an hour-long lived thing. Now that we're below threshold and again, this below threshold is like, it's like a few people in the lab, like poking the experiment and then like making sure the pulse comes out in the right time on the oscilloscope. And sometimes it looks weird. Then you change a bug and then, now it looks good again. So it's like that style of thing has been able to get us to a factor of 2 below the threshold. With relatively straightforward improvements, I think we should be able to get to a factor of 5 below the threshold. And if you do that on several thousand qubits, then you can get to really long-lived many cycles of logical error. That sounds nice in theory, but now, doing it in practice, of course, requires a lot of things. But for it to be a very, very long road to get to that would require some sort of major unforeseen bottleneck.
Okay, any more questions from the, sorry.
Yeah, an hour is amazing, but I'm not sure, those applications that we're aiming at are going to be feasible within an hour, so we have to look at even longer time scales. So eventually, we'll see.
Okay, are there any more questions from the audience? All right, Umesh.
So, do you think that we already have, or when do you think this will tip over from being technology to being science? The fact that quantum computers are being built, and when, with sufficient fault tolerance and so on, when do you think this will become new science, as in, you're exploring something much more fundamental, or when would it be considered to be that?
We have this internal thing that, it would be great if one day these papers that get into like these shiny journals don't have to say like on a quantum computer in the title, and it's just like a novel discovery. And I do think we're actually closer than we probably expect, in that I think it's probably unlikely there is some significant, useful, scientifically relevant quantum advantage in the NISQ era that's like provable quantum advantage, and like you could not have ever maybe written some custom simulator to find it. But I think we're much closer to the sort of realistic quantum advantage of, if you have a programmable quantum computer that's able to do a number of things, and each time you change some parameters and make a new classical simulator to try to spoof it, it takes somebody a lot of time to focus on this one particular instance, and that time you could have done many other things. Like we've already had a few of these NIST experiments at Google that were surprising to us. Like the outcome was not what we expected. And then once we saw the outcome, we went back and you're like, oh, okay, actually this does make sense. But nobody knew that this was like, there's this paper Alexi Morvan and others wrote where they were just like surprised by the stability of a particular state. Whether that counts as science in its own right is up for debate. But I think we're kind of entering this era where the surprises might get bigger.
I would also agree that I feel like we've done pretty interesting quantum simulations where we've learned something. I think they've all been like baby discoveries in many different ways. Like you could have discovered it on a classical computer, or you could have. But okay, since it's a fault tolerance session, something I would personally find really interesting is I would really like to do exponentially long circuits where we see emergent particles emerge and orbit each other from an ADS CFT perspective. That would be super, super interesting. That would just be so fun. So that is an example application where maybe we don't need that many qubits, but if we can go to exponentially long times by exponentially suppressing errors, you could see some pretty funky physics that may not exist anywhere else on Earth because everything always has some finite coherence time. But once you can, use error correction to go to exponentially long times, that's an example of a place where we might start to see new science before we get to really, really large numbers. That's at least the one I find really interesting.
Yeah, I kind of like what Dripto was saying. Maybe once a scientist can sit down and send their quantum program to some machine somewhere, and they don't have to think about how to compile their gates down so it fits on the tiny device and what errors it has, then it will start to feel more like pure science and not also engineering where you have to like fiddle with all the circuitry and stuff. Just like you would use a classical computer and you run your simulations and you don't really care what is happening under the hood, right? There's very smart compilers that have been built over the past few decades. That would be very neat. Yeah.
There's one question in the back.
Hi, thanks for the next panel. I think I understand your bias, but what do you think of the completely alternative platforms like potentially, qubits or fermions or bosons, like not qubits? Like, what do you think? Is there any room there?
I think it's just hard. I mean, it's not like I don't think it's necessarily wrong or not going to work. I think it's just we're having enough of a hard time making qubits do the things we want them to do at the scales we want. So I'm not sure if like Q-trits is.
Will be probably intrinsically harder than qubits.
I think Q-dits at least are intrinsically harder. Fermions, bosons, maybe there's nothing fundamental saying that, but it just seems hard. I don't know.
I would love if there was a really creative usage of qubits because there's definitely like native qubits in both our system and also other systems. So I would personally be thrilled about that. But the thing that has always been, because it seems like really interesting science, the thing I always get hung up on is why not, like if you have a 3-level or 4-level system, why did you make it with a qubit as opposed to just 2 qubits? That's always the, and I've yet to find something that was obviously much better, but it could be that I'm not looking in the right spots. But if there was an interesting application of a qubit, I think that would be really fun because there's all these levels in the atom and it would be really fun to use them for something useful.
Yeah, I don't have much to add to that.
Okay, are there more questions from the audience? So one other question I had in mind was asking you about milestones, but now that I'm sitting here, I kind of, maybe I hope it's not too controversial, but maybe I would be curious to hear from you what you think the person to your right next milestone should be.
Ooh.
And then cyclic. So what do you want to see? I don't know. You can be nice. Like
I mean, you mentioned the latency in the decoder. Maybe push down the latency for the decoding.
Yeah, and I think that definitely is one that we're definitely working on. I think the next, results will definitely try to have that lower. I think that's sort of similar vein of like something you kind of already talked about. You showed a lot of these circuits that, you have a large number of qubits now, so you have multiple logical qubits. I think having one of these algorithms, using all the theoretical pieces you've built and like running an algorithm that like sort of like a well-known algorithm, not just like a random circuit thing, and then decoding through it and showing that in like a structured circuit, you're able to see all the things you see and like all these reliable logical operators and everything, it all works out, I think would be a nice proof of concept. Because some of those decoding things feel like there's parts of it that feel illegal, And so if you can just prove they're not by just doing it, that would, I think, be a great proof of concept that should be within reach.
I think I would be thrilled to see. So, okay, if you're sticking to these bicycle codes, I would be thrilled to see the bicycle codes. Okay. So that would be a cool milestone. I would flip it and say what I think the milestone should be to try to come up with a way to control all these qubits in parallel, because that would make it way easier to get to large scales. But I understand that there's challenges with that.
Yeah, I mean, IBM is going to build a small baby version of the gross code in the coming year or so, 2026. So hopefully we'll see a demonstration, and we're very excited to see how that's going to pan out. And then in parallel to that, of course, we'll be working on the parallel control aspects.
I think we.
Okay. Great. Great. And then maybe lastly, maybe just like one more round. The third question is somewhat like vague by design. So what kind of evidence would you need to kind of significantly change your strategy? And again, I kind of keep it vague what evidence means and what kind of strategy means. Like, I know maybe Dolef, you will kind of abandon neutral atoms and go ion or something like this, or superconducting. So is there anything that would kind of completely make you kind of abandon LDPC codes?
I guess, I'm gonna sidestep the LDPC code because we've talked a lot about changing your code. For me, I think the fault-tolerant community has focused a lot on this so-called poly-based computation scheme, and there are very good reasons to use it because it's so simple and effective. Like, I'm really keen to see if there are significant steps forward that can be made, and this could change entirely what kind of like software pipeline you would need to compile your applications to the device. Like, maybe you have large-scale algorithms in mind you want to run, and right now we have an automated way maybe to compile Clifford plus T to an architecture, but you lose all the parallelism that's present in the original circuit. I would like to see novel ways of compiling such algorithms that maintain the parallelism, that can minimize the amount of entanglement needed to run your circuit, and they don't use too many T states, all these kind of things. Like, there are many ways you could optimize, but that could change significantly how we compile for such architectures.
Yeah, I mean, to follow kind of the theme I've been pushing sort of the whole day of like experiment and theory kind of working together. I think at Google, our theory is often very guided by what the experimentalists say they're doing, or like could be a thing they could consider doing if we can find a reason to justify it. And so I think if there's some large experimental breakthrough, whether it's like a long-range coupler that seems like it's on par with short-range couplers, or some other architectural change that the experimentalists say like they feel very confident they're able to implement, and they just go and build one, it's much easier for us as theorists to redirect. Like, I don't need to throw out what I did yesterday to just open up a new tab on my laptop and do something else there. And so I think if the experimentalists feel like they're able to give us a new fun toy, we would all jump on the opportunity to play with something else while still feeling justified in doing so.
So Okay, my first answer would be my go-to answer of that if there was a way to do large-scale parallel control in something like superconducting circuits, that would be so enticing because then you could print a chip that has 10,000 qubits and then like in a university lab, make like a large 2D cluster state. That would be very compelling. I think more realistically, I feel like it's quite unlikely that this question of like superconducting qubits, ions, atoms is going to like resolve in the next few years because it seems quite likely that all these systems are going to get to extremely low error rates with error correction. And that's going to be so impressive that it's going to be really hard to convince people to stop doing that. I think something I'm always open to is that there's some really, really hilarious unforeseen application of quantum computers that emerges in the coming years that really changes our perspective on what we think we should be focusing on. And that's really hard to foresee. But that would be a really interesting reason that, oh, there's just some amazing application that we come up with that's like actually really pressing, and somehow that changes the motivation in the near term. I don't know.
Okay, very good. All right, so that was our panel. Yeah, please thank our speakers and panelists. Yeah, that was it for Torrents for today. But we do have a reception outside, so yeah, please join us just outside the room.